4.4 Modeling and Optimization. Your objectives for this lesson are to use derivatives to model problems and to use derivatives to optimize problems. Okay, so optimizing means to maximize or minimize some aspect of something. That thing is whatever you happen to be optimizing. In our example, this will be volume. So we only have one example for this lesson. Example 1. An open top box is to be made by cutting congruent squares of side length x from the corners of a 20 by 25 sheet of tin and bending up the sides. How large should the square be to make the box hold as much as possible? And what is the resulting maximum volume? So let's start by drawing a model of this. If I have this sheet here, this would be 25 inches by 20 inches. And in order to make this box, I'm going to cut out squares from the corners. So I could have one right here. And I would cut the same one from each corner. Okay, so, and I'm not sure how big this square is. That is the question. How large should the square be? So I'm going to call the side length of that x. And since all the squares are the same size, I know that each of these lengths is x. Okay, so then when I go to fold up the sides of my box, I'm going to end up with this. Okay, so fold up the edges. One more. Okay, and you can see, since these parts aren't here, really I'm folding on this dotted line and here. Which means that the height of the box is this x. So this is x. This shorter side of the box is 20 minus, well, I subtracted an x, I lost x inches there, lost x inches there, so I lost 2x total. And it's 25 inches long minus 2x, so 25 minus 2x in this direction. So this is my box, which means that the volume, remember the volume of a rectangular prism is the length times the width times the height. So V as a function of x is equal to x times 20 minus 2x times 25 minus 2x. And now we're going to solve this two ways. The first way will be by graphing. And first let me restrict my x values here. So I know x can't be 0 because this whole volume would be 0. But this here and this one also, I want to be greater than 0 because otherwise I'm going to have a negative volume, and I know if I have a box, I'm going to have a positive volume. So x must be greater than 10, or sorry, x must be less than 10. But from this, I know that x must be greater than 0, because here x has to be greater than 0. If I were to solve this one out, I get x is less than 12.5, but this is already covered by saying x is less than 10. So really this is extraneous, we don't need that. So I'm going to graph, and this will be my window for my x values. So plugging this into y equals, I have x times 20 minus 2x times 25 minus 2x. And graphing, I think I'm going to have to change my window. So I said x min is going to be 0. Let's make y max bigger though. So from 0 to, I don't know, 800. Okay, so I'm almost there. I need to go a little bit bigger on my y so that I can see the top of this graph. Okay, there it is. So maybe I should do a little bigger so the numbers don't get in the way. That's a little better. Okay, so if I wanted to find the maximum volume, that's the y values here. So I'm going to hit second trace. 4 is maximum. Enter my left bound. Scroll over, enter my right bound, and I'm at about 3.681, comma 820.528. So my maximum volume is about 821 cubic inches. And that happens when x is about 3.681 inches. Okay, but we want to do this analytically also, because you're not always going to have your calculator. And we're going to do that by beginning to multiply this out. So multiply, FOIL it out. So 20 times 25 is 500, minus 2 times 20 is 40x, minus 2 times 25 is 50x, plus 4x squared. Okay, now I need to distribute this x. But before that, I'm going to combine some like terms. So these two become a negative 90x. I'm also going to reorder. So x times 4x squared is 4x cubed minus 90x squared plus 500x. So this is my volume model. And I want to find the maximum of this. So I'm going to find the derivative, so I can set the derivative equal to 0. So I have 12x squared minus 180x plus 500. Not too bad so far. To solve this, remember I'm going to set it equal to 0. And I don't even want to try to factor this because I have some big numbers up here. So I'm going to label my A, B, and C and use the quadratic formula. So remember that is x equals the opposite of B plus or minus square root B squared minus 4AC all over 2A. Okay, so this is the quadratic formula. Okay, so x equals, opposite of b is 180 plus minus square root negative 180 squared minus 4 times 12 times 500. Okay. All over 2 times 12. Okay. So 180 plus or minus 180, negative 180 squared is 32400 minus 4 times 12 times 500 is 24000. Okay, all over 24. Okay, so 180 plus minus the square root of, and 32,400 minus 24,000 is 8,400. So square root of 8,400 over 24. And at this point, I'm going to break this up and I'm going to use my calculator to evaluate the two values here. So I have 180 plus the square root of 8,400 divided by 24, and 180 minus the square root of 8,400 divided by 24. So for the first one, we get 11.319. For the second, we get 3.681. Okay. And now, looking at these, I already decided the domain of my function was from 0 to 10. And 11 will not work here because x is between 0 and 10. So this is the only person I am looking at, 3.681. This is telling me the size of the squares. So this is the side length of a square that I'm going to cut out for the edge, which is from back up here. So you see x is the side length of the square. But I don't just want the side length of the square, I also want to know the volume. So I'm going to plug this into the volume formula. So remember, well, v of x was equal to 4x cubed minus 90x squared plus 500x. And what you should do here, instead of approximating your answer, so if you have this on your calculator right now, you have the 3.681, hit the store button and then x, so store it as x. And now to evaluate v of x, well, I already have that in my calculator, so I'm going to go to y-vars, so vars, y-vars, function, y1. I want to evaluate y1 of my x. Enter, and I get 820.528. So V of 3.681 equals 820.528. Okay. And that would be inches cubed. So this is the volume. Which was the second part of the question. If you wanted to, I could circle this part here too. But I should label the unit as inches. I could also write a nice concluding sentence and say cut out squares that are about 3.681 inches on a side. Give the maximum volume of about 820.528 cubic inches. So this is my answer. And that is all for 4.4.